Hey everybody, I wanted to discuss basic feasible solutions in linear programming. This will be from the algebraic perspective, but then next time I'll describe how you should think of basic feasible solutions from the geometric perspective. Spoiler alert, they're the vertices of the feasible region. So this is the last machinery we need before defining and describing the simplex method. In the last video, we saw that any linear program can be written in equational form. Equational form means you're maximizing something. You have only equality constraints, except for non-negativity constraints. And you can always put a linear program in this form, for example, by introducing slack variables, etc. We're only going to consider linear programs in equational form satisfying two extra additional assumptions, these two bullet points here. We want the matrix equality to have at least one solution, since otherwise it's easy to see that the corresponding linear program is infeasible. All right, so that's an easy check. You're given a linear program. Just do some Gaussian elimination after you put it in equational form. If this matrix equation has no solutions, then you know your program's infeasible. Secondly, we're also going to assume that the rows of this matrix A are linearly independent. You'll remember the rows of matrix A give us our equality constraints. And if they're linearly dependent, you can just remove some of the redundant ones without changing the equation. So we're assuming that the rows of A are linearly independent, since otherwise we can find and delete rows from A without changing the linear program at all. Okay, so those are just two additional assumptions on equational form, which allow us to define and work with basic feasible solutions. Okay. So a feasible solution, meaning a solution satisfying these constraints, is basic if there's an M element subset B. Remember, M is the number of rows of matrix A. N is the number of columns. So N is the number of variables in this vector X. So a feasible solution is basic if there's an M element set B such that the matrix A restricted to B is non-singular. I'll have to tell you what this means, i.e. the columns indexed by B are independent, and if all of the other entries of this vector are 0. Okay, that's a little confusing, so let me describe it for you on an example. So pretend our matrix A is this 2x5 matrix. And so X is a vector of length 5. And B, this vector B, is 14, 7. So remember, one of our constraints in our linear program was simply AX equals B. All right, so this is a 2x5 matrix. So M is 2 and N is 5. We want to find B. It's a subset of 1, 2, 3, 4, 5 that has size 2. Okay, so we want to find, we'll call it a basis, capital B, that has size 2, and it's a subset of the numbers from 1 up to 5. All right, so this basis B will actually encode rows of A. So we're looking at the second row and the fourth row, sorry, columns of A. We're looking at the second column and the fourth column because my basis B tells me to look at those two columns. Let me tell you what A sub B is in this case. A sub B is the matrix that I get by taking matrix A and only restricting to the columns in this basis B. So when I restrict to the second and the fourth columns, I just get this square matrix 5, 1, 4, 5. Okay, so this vector x here is a basic feasible solution. Let's go through and check why. So first, we need a 2-element set from the numbers 1 up through 5, such that the square matrix, when I restrict to those 2 columns, is non-singular. And indeed, when I restrict to columns 2 and 4 in my matrix A, this is a non-singular matrix. It has non-zero determinant. In other words, these 2 columns are linearly independent. And furthermore, what do we need? We need all of the entries of this vector x besides the second and the fourth to be 0. So the second and the fourth entries could be potentially non-zero, but all of the other entries have to be equal to 0. Okay. And then furthermore, I mean, that's what it means for x to be basic. Furthermore, x just needs to be a feasible solution, which means it solves the equation ax equals b, and it does. When I multiply this matrix capital A by this vector x, I get 2 times the second column plus 1 times the fourth column, and that gives me 2 times 5 plus 4 is 14, and 2 times 1 plus 5 is indeed 7. Okay, so that's why x is a solution to ax equals b. It's feasible, furthermore, because it's non-negative, right? We have these non-negativity constraints. And it's basic because it has a corresponding basis. 2 of my columns of A form a basis for 2D, and my vector x is non-zero only in those corresponding entries. So yeah, we call B a basis. It's a slight abuse of notation. B is a subset of the numbers from 1 up to n, but we really think of B as corresponding to the rows of this matrix A, and this requirement that, corresponding to the columns of matrix A. And this requirement that the resulting matrix is non-singular is just exactly saying that those columns of matrix A are linearly independent. They form a basis for m-dimensional space. All right. Let's do another example. I have the same matrix capital A, but I've changed this vector B again in my equation ax equals b. So let me show you another basic feasible solution. It's this vector 0, 2, 0, 0, 0. It solves the equation ax equals b because when I multiply matrix A by this vector, I just get twice the second column, and 2 times that column is indeed 10, 2. Okay. Here, however, there's many different choices you could choose for the basis that might be associated with this basic feasible solution x. So you definitely need column 2 to be in your basis, right? Because this entry of the vector is non-zero. That was one of our definitions. You know, if the entry is non-zero, then J has to be in your basis. But after I select this column 2 to be in my basis, I could select any other column. I could select column 1, or I could select column 3, or 4, or 5. And all of these form bases. So if I take the second column with either the first, or the third, or the fourth, or the fifth, that is a basis for 2D. So what we've seen is we have a basic feasible solution that might correspond to multiple different bases, capital B. And that's our moral. A basic feasible solution X does not determine a basis B, right? It might determine several possible bases, capital B. This brings me to my next point. By contrast, a basis B does determine at most one basic feasible solution, okay? So if I tell you a basic feasible solution, there might be several corresponding bases. By contrast, if I tell you a single basis, that gives you at most one basic feasible solution. So let's do this on the above example. Let me specify a different basis, 1, 4. So I look at column 1 and column 4. Those are indeed linearly independent. So 1, 4 is a basis here. And now I'm going to show you how to solve for the corresponding basic feasible solution X. So to be a basic feasible solution, it can only be non-zero in its first and fourth entries. So in all the other entries, it better be 0. It's 0 in the second entry, third entry, and the fifth entry. Well, let's just give an arbitrary name to the first and fourth entries, x1 and x4 are good names. Okay, so matrix A times X is supposed to be equal to this vector B, which in this example is 10, 2. I can write A times X as the square matrix AB times x1, x4. That's just because when I multiply matrix A by this vector, what that's doing is it's taking x1 copies of the first column, 0 copies of the second column, 0 copies of the third column, x4 copies of the fourth column, and 0 copies of the last column. So clearly, we're only taking a linear combination of x1 copies of the first column and x4 copies of the fourth column, right? So I could instead just write this as the first column and the fourth column times x1, x4. And this is exactly what the matrix AB is. B is this basis corresponding to the first and fourth columns. So AB means from matrix A, take the first and fourth columns to get exactly this square matrix. All right, you know, I could write this as the vector. I'm just doing the matrix multiplication, x1 plus 4x4 and 5x4 on the bottom. Okay. At this point, we can solve for x1 and x4. We have this system of 2 equations and 2 unknowns. This bit has to equal 10. This bit has to equal 2, right? AB is a non-singular matrix, so I could multiply by its inverse. That might be one way to solve it. Okay, there's many ways to solve a system of 2 equations and 2 unknowns. In this example, I can immediately solve for x4 using the second equation. So x4 had better be equal to 2/5 in order for 5 times x4 to equal 2. And then now I can plug in for x4. So 4 times 2/5 is 8/5. I need to get up to 10, so I need to get up to 50/5. So x1 had better be equal to the remaining 42/5. So that I have 42/5 plus 8 more fifths equaling 50/5 or 10. All right, so what we're really using here is we're using the fact that this square matrix AB is non-singular. Okay, that was part of the definition of a basic feasible solution. The basis B, by definition, a basis B has to correspond to linearly independent columns of matrix A. So once we pick a basis, if it's indeed a basis, then we have to set these variables to zero. The variables in your basis are variables, but you can solve for those variables uniquely using the fact that your matrix is invertible. Okay, so I said that a basis determines at most one basic feasible solution x, which I've solved for here, once I plug in the values of x1 and x4. You can also get that a basis might determine 0 basic feasible solutions. So let me give you an example like that. I'm using the same matrix, the same vector little b, but I'm just choosing a different basis. So I'm choosing the basis, which is the 3rd and the 4th columns. And that is indeed a basis because those two columns are linearly independent. Okay, so let's set up the equation. So we set tend to, let me do this up. We set tend to, that's this vector b, that has to equal a times x. And then another way to write a times x is ab times x3, x4. So x here has to be 0 in the 1st, 2nd, and 5th coordinates. But because my basis is 3, 4, it could potentially be non-zero in the 3rd and 4th coordinates. Okay, so that's where this equality is coming from. A times x, well, x is 0 in the 1st, 2nd, and 5th columns. So I don't need them when I'm writing a times x, right? A times x is some linear combination of the columns of A, but I have 0 times the 1st column, 0 times the 2nd column, 0 times the last column. I only need the 3rd and 4th columns, and that's what's stored exactly in this matrix AB. It's probably better if I just write it. This matrix AB, I just look at the 3rd and 4th columns to get 3, 3, 4, 5 times x3, x4. All right, let's multiply this out. This gives me the vector 3x3 plus 4x4 and 3x3 plus 5x4. So since AB is invertible, one way you could solve for x3 and x4 is just multiply by the inverse of AB on both sides. But okay, this is not a very hard system of 2 equations to solve. If I had to solve this, I would take the 2nd row and subtract the 1st row. And if I took the 2nd row and then subtracted the 1st row, I would get 2 minus 10, which is -8. And that would be equal to, the 2nd row subtracted the 1st row would just be 1 times x4. Okay, so I've solved for x4, it's -8. And from there, you can solve for x3. I think that implies that x3 has to equal 42/3, it turns out. Okay, so I had a basis, 3, 4. It was indeed a basis. I solved for the corresponding basic feasible solution. But what do I notice? One of the entries is negative. So this is not even a feasible solution, right? In my linear program in equational form, my vector has to be of non-negative entries. Most of the entries were non-negative, okay, but this 4th entry, which is -8, is negative. So I don't even have a feasible solution. So does this basis yield a basic feasible solution X? No. This basis 3, 4 does not yield a basic feasible solution since the corresponding X is not non-negative. And hence it's not even a feasible solution. So I apologize for the double negatives, not non-negative, but I don't know how to say that otherwise. Okay, trick question. If I let capital B be 3, 5, so I'm looking at the third and fifth columns, does that yield a basic feasible solution? No, we're sunk from the start. The set capital B, which was the third and fifth columns, doesn't even yield a basis. Just because when I look at the square matrix formed by taking the third and the fifth columns, I get a singular matrix, a matrix with determinant 0. Okay, so that's an introduction to what a basic feasible solution is. An important theorem says that if an optimal solution exists to this linear program here written in equational form, then there is also an optimal basic feasible solution. Which we abbreviate as BFS. Okay, so we'll later see 2 proofs of this. One proof of this follows from the correctness of the simplex method. How the simplex method works is you're going to move along vertices of your polytope, or in other words, you're going to move along basic feasible solutions until you get to an optimal one. And in proving that the simplex method works, you prove that if an optimum is attained on your polytope, it's also obtained on a vertex, or in other words, on a basic feasible solution, as we'll see. Okay, so I also sort of outlined this second argument for the theorem. It follows since every vertex of a feasible region corresponds to a basic feasible solution, and a linear program or a linear function optimized on a polytope, it might be optimized only at a vertex, say if I'm moving in that direction, or it might be optimized along an entire face of a polytope. But even if it's optimized along an entire face, it's still optimized at least one vertex. This gives us an impractical algorithm for solving linear programs. So I could look at all possible candidate bases. So from the set of size n, I look at all subsets of size m. Those are all my candidate bases. When I have a candidate basis B, if the corresponding columns are linearly independent, I can solve for the unique corresponding potential basic feasible solution. It's only a feasible solution if it's non-negative, okay? But then I can just look at what's the value of my optimization function on all these candidates. I have at most n choose m candidates, so I can just check the value of the optimization function on those candidates. So that's a valid algorithm. It's just very impractical, as n and m grow, n choose m can get very large. And so we want a program, or we want an algorithm that's going to run in, say, closer to linear time or polynomial time. That'd be a faster algorithm, as opposed to this one that would require you to check an exponential number of candidate solutions. All right, so fantastic. That was my introduction to basic feasible solutions, which are the building blocks of the simplex method. And I gave you an algebraic definition and description of basic feasible solutions. And next time, we'll see how they correspond exactly to a geometric concept, namely the vertices of the convex polytope, defining the feasible region. Thanks.